Today in physics, we'll be discussing the process of leaving the surface of a hemisphere or a sphere. So we have our hemisphere of radius r, and we have an object at rest at the top of this hemisphere. Now we're going to give it a really tiny push so it starts moving down. But initially, we're going to say that it pretty much starts at rest. Now there's no friction involved, but we want to figure out at what height will this object leave the surface of the hemisphere and start doing its own thing. So this is where it starts out from rest. But it might be more helpful when we're figuring out where it actually leaves the surface of the hemisphere to draw it so it depends on an angle. And let me do it right here. So we have our object here, and the angle that the object makes with the vertical, which is the first dotted line, we'll call this angle theta. Now we have two forces and only two forces, since we're neglecting friction and air resistance, that are acting on this object. We have gravity. So let's say this object has a mass of m. So the gravitational force acting upon it is mg. Now we can decompose it by looking at the angle theta and figuring out the two components of gravity, where one is perpendicular to the surface of the hemisphere and one is tangent to the surface of the hemisphere. So this is the component that is tangent, and this is the component that is perpendicular to the surface. So we can see that this angle seems to be theta. So we also know that the tangent component of the gravitational force is perpendicular to this line, to the diagonal line which forms the two thetas. So we can conclude that this angle would be 90 minus theta, and so the angle facing the tangent component would be theta. So the tangent component turns out to be mg times sine of theta, and the perpendicular to the surface component turns out to be mg times cosine of theta. Now the other force that is acting on this object is the normal force. So let's call it Fn, the normal force. And it's acting along the opposite direction and acts against mg times cosine of theta, the component of gravity perpendicular to the surface. Now, let's define what we're trying to find. We'll call this h, and we'll define h as the height above the ground, so where we define this bottom place as the ground, where the object will leave the surface. So it leaves the surface of our hemisphere. While this object is still on the surface of the hemisphere, it's undergoing centripetal acceleration. So it has to be subject to some sort of centripetal force. So the required force is m times a centripetal, the centripetal acceleration, and the centripetal acceleration is equal to the velocity squared over the radius of the circular path, in this case r, and this is equal to, we know that the centripetal force must act on this object, and it must point towards the middle of the hemisphere, or the middle of the sphere, namely here. And we can see that along this same direction we have an actual force of mg times cosine of theta, while a force that goes the opposite direction is f of n. Now we can write this equality, since the centripetal force is not an actual force, it's the amount of force that is required in order for this object to undergo circular motion. The actual forces that are acting upon this object are the components of gravity and the normal force. However, once we know that the object leaves the surface of the sphere, namely once it reaches the height h, it no longer is in contact with the surface of the sphere. So that means since the normal force is a contact force, once it's not in contact, the normal force becomes 0. So we can then see that mv squared over r must be equal to mg times cosine of theta. Now we can solve for theta to get cosine of theta is equal to v squared over r and divide that by g. Okay, so now we found out this relationship, but we don't know what v squared is and we don't know what cosine of theta is. Now we can use energy conservation in order to figure out what v is at the point when the object leaves the surface of the sphere or the hemisphere. Since there are no non-conservative forces that are acting on our object, such as friction or air resistance. Now, when we're considering our potential energy and our kinetic energy, we can consider just a portion of the sphere and hemisphere. We know that if this is the center of the sphere and hemisphere, and this is the top, we know that this distance is r, and let this be the point where the object leaves the surface of the sphere, so namely h, which is how we define h. Then the vertical distance that this object actually travels is just r minus h, when it goes from rest to the point where it leaves the surface of the sphere. So at this bottom line, we define that as our zero potential energy for gravity, and at the beginning we consider it to be at rest, so it has no kinetic energy. Then we can write our equation to be m times g times the distance, namely r minus h, is equivalent to the kinetic energy at the point where it leaves the sphere, namely 1/2 mv squared. Then we can see that v squared, where we divide by m and multiply by 2 on both sides, is just 2 times g times r minus h. Okay, now we're a step closer to figuring out what h is, but we still don't know what cosine of theta is. Well, if we look at a portion of the circle of the hemisphere or the sphere, once again, we earlier defined theta as the angle from the horizontal, and if we draw from the vertical, and if we draw another vertical line, we can see that this is theta. Now we want to find the theta at the point where the object leaves the surface of the sphere. So let this be the point where the object suddenly leaves the surface of the sphere. Now we want to find what cosine of theta is. By looking at it geometrically, we know that this long diagonal line is just the radius of the sphere or hemisphere. And earlier we defined this height to be h, since h is the distance above the ground where the object leaves the surface of the sphere. So then we can see that cosine of theta is equal to so-and-so adjacent over hypotenuse, or in this case just h over r. Now we can replace cosine of theta with h over r, and we can replace v squared with what we figured out from energy conservation. So we find that cosine of theta is h over r, and v squared is 2 times g times r minus h, and we want to divide that by rg. Now we can see that we can cancel out the g's on the right side to get this equation. And if we multiply by r on both sides, we get that h is equal to 2 times r minus h. And so solving for h, we get that 3h is equal to 2r, or h is equal to 2/3 the height of r. Another way which we could have figured out h was by how we define h. In this case, we define h to be the height above the ground at which the object leaves the surface of the sphere, but we also could have defined h as the height beneath the top part of the sphere or hemisphere. So namely, here, when this is the object at rest initially and this is the object when it leaves the surface of the sphere, we could have defined this height to be h. In that case, cosine of theta would have turned out to be r minus h over r, and we would have found that v squared would equal to 2 times g times h. However, if we put these two new values into our equation here of their relationship, namely cosine of theta is equal to v squared over rg, we would have found that we would have gotten the same answer. However, in this case, we would not have gotten that h would equal to 2/3 of r, since we're defining h differently. Rather, we would get that h is equal to 1/3 of r. But either way, when we look at how we define h, we always have that at the point where this object leaves the surface of the sphere, the vertical distance from the very top of the sphere is 1/3 r, and the vertical distance from that point to the ground is 2/3 r. And so we find that these two ways of defining h, turn out to give you the same physical answer, just looking at it from different perspectives.